The second introductory lesson deals with the representation of algorithms. The specification of digital systems by means of algorithms is a central aspect of our course. And many times, in order to define algorithms, we will use sequences of instructions very similar to programming language instructions. So, if you already know some programming language such as C or Java, the contents of this lesson will sound to you very familiar. An algorithm is a sequence of operations whose objective is the solution of some problem, for example, a complex computation or the control of some process. For example, in the preceding lesson about numeration systems, we described addition and difference algorithms with binary numbers. The result of an algorithm execution must be independent of the chosen type of algorithm representation. Some common representation methods are natural language, flow diagrams, programming languages, and also something not so well defined called pseudocode. It is similar to programming language, but more informal. It uses a mix of natural language sentences, of programming language instructions, and also of some key words that define basic structures. Two important aspects of programming languages, and thus also of pseudocode, are the available operations and the control structures. Many times, all along our course, assignment instructions will be represented in this form, similar to an arrow. Given variable x, y, and z, this kind of assignment means that x receives the value 15, and this one means that the current value of x is replaced by the result of computing 2x plus y plus z. This symbol corresponds to the simple equal to symbol in C. We use this other symbol because it is the signal assignment symbol in VHDL, the hardware description language we used in this course. The comparison operators are the classical ones: smaller than, greater than, equal to, smaller than or equal to, greater than or equal to, and different from. Sometimes logic operators will be used. For example, within a condition, we could write something like if x is even and x is greater than or equal to 8, then some operations. This means that x belongs to the set 8, 10, 12, 14, and so on. Another logic operator, apart from and or, is not. An example, x is even is the same as not x is odd. The arithmetic operators are the classical ones: sum, difference, product, and division. Now some comments about control structures. We will use selection or branching instructions such as this one. If some condition holds, then a sequence of actions, the corresponding diagram is this one. Or if some condition holds, then a first sequence of actions, else another sequence of actions. Another example, this one. If a first condition holds, then some action or some sequence of actions. Else, if a second condition holds, then another action or another sequence of actions. Another way to define selections is the case statement. Assume that a variable x can take 4 values called value 1, value 2, value 3, and value 4. Then sequences of actions can be selected in function of the value of x. In the case that x is equal to value 1, then some action or some sequence of actions. In the case that x is equal to some value 2, then another action, and so on, with value 3 and value 4. Let us see some examples. Assume that you must compute while equal to x divided by 2, but round it, so that the result is an integer, and that you round towards 0. That means that if x is positive, then y will be the greatest integer smaller than or equal to x divided by 2. And if x is negative, then y is equal to the smallest integer greater than or equal to x divided by 2. I mean that if x is equal to 10, then y will be equal to 5. If it is equal to minus 10, minus 5. If x is equal to, let us say, 7, then y will be equal to 3. Observe that 3 is 7 minus 1 divided by 2. But if x is equal to minus 7, the result must be minus 3. And observe that minus 3 is minus 7 plus 1 divided by 2. So that the algorithm could be the following one. If x is even, then y is x divided by 2. Else, if, so x is odd, but if furthermore x is negative, then in the second case, y must be equal to x plus 1 divided by 2. And in the third case, y will be equal to x minus 1 divided by 2. And if. This is a first example of an algorithm with some branching. Let us see a second example. Assume that x is a decimal digit and that you want to generate the binary representation of x. Then a simple table could be defined as follows with a case statement. Case x is, then all the cases are when 0, then y will be equal to 0, 0, 0, 0. When x is equal to 1, then y will be equal to 0, 0, 0, 1, and so on. up to when 9, then while will be equal to 1001. And that's it. End case. Another important type of control structure is iteration. Here we see two examples, the while loop and the for loop. While loop, whose structure is while some condition holds, then execute a sequence of action. And the diagram is this one. And another example, for, here is the name of some variable in some range between min and max, then a loop that includes a set of instructions. Let us see an example. Assume that you have defined previously vectors A with, let us say, 8 components, A0, A1, and so on, up to A7, and another vector X, also with 8 components, all numbers, integer for example, and you want to compute y equal to A0 times X0 plus A1 times X1 plus and so on up to A7 times X7. Then you could define the following algorithm. An accumulator variable x initially equal to 0, and then a loop for I in range 0 to 7, loop ac replaced by the previous value of ac plus the product ai times xi, and that's all, end loop. So this small algorithm computes this expression. A last type of programming language instruction that we will use in our course is the call to procedures. A procedure, also called a subroutine, is a piece of program, a sequence of instructions with operations and control structures that execute some algorithm. Then a name and a set of parameters are associated to every procedure, and procedures can be called one or several times within the main program, and when called, values are given to its parameters. Let us see an example. Assume that we want to compute z equal to a times the square root of x plus b times the square root of y. Then, first, we could define an algorithm that computes the square root of a number with an accuracy of n digits, for example, and encapsulate this algorithm within a procedure square root. So we will say procedure square root with parameters x, y, and n is, and then a set of instructions that computes y equal to the square root of x with the n fractionary digits and procedure or n square root. Then the main algorithm will be the following. Square root, we make a call to the square root procedure with parameters x, a new variable u, and for example 16, this will compute u equal to the square root of x with 16 fractionary digits. After, we could replace u by the product of a by u, so that u will be equal to a times the square root of x. After that, we call again the square root procedure, but in this case with other parameter, while b, v, and 16, so that v now is equal to the square root of while with 16 fractionary digits. Next instruction, we substitute v by v, b times v, so that now v is equal to b times the square root of while, and finally we compute the sum of u and v. So as you can see, we have called 2 times the procedure square root. Summary. In this lesson, we have presented an algorithm representation language, the pseudocode, and have defined operations and control structures.